Hello, welcome to lecture 28. Today we are going to discuss path integral for gauge theories, basically gauge fields. So we have noticed till now, and as was promised much earlier also, is that when we do path integrals for scalars, for example, so if you write the quadratic piece, then the coefficient of the quadratic piece can be written as an operator, and the scalar propagator turn out to be the inverse of that operator in the momentum space. Likewise, for the fermion case, is psi bar, here is psi, and an operator, kinetic operator, is sitting in between. So I can say coefficient of the quadratic piece, and that thing in inverse appears for the fermion propagator in the momentum space. Okay, so basically the inverse of these operators is what has been coming out as a propagator. And similar thing one could have done for the gauge field, and in fact that was the argument I gave without having the path integral backing when we are talking about the gauge quantization, the canonical quantization of gauge theory. So we noticed that if we follow the similar stuff, the gauge propagator will be inverse of this p mu nu, but it turns out that p mu nu was a projection operator and hence non-invertible, and that led us to the gauge fixing. Okay, so this is what we know. This issue with the gauge theory that it requires a gauge fixing is known, and path integral way of doing it would also require gauge fixing, and we'll see how we go about it. So this path integral measure that's written over here, so this is the path integral over entire configuration space. Okay, so it doesn't distinguish between anything. So this what we know about the configuration space is that the gauge orbits connect the physically equivalent configuration. All the configuration that can be connected to each other by gauge transformation are said to lie on the same gauge orbit. And the configuration, the full configuration space is physically equivalent configurations, a physically inequivalent configuration, I should say, because they cannot be connected by gauge transformation. That a set of physically inequivalent configuration you can choose, and then do a direct product with the gauge orbits. Okay, so to say the gauge transformation parameter. So this particular product will give me the full configuration space, and that is exactly what we'll have to do in the reverse order. We have the full configuration space. What we want is to segregate these two things. The goal of gauge fixing is to pick out a single copy of each physically inequivalent configuration. That was the purpose of the gauge fixing condition, so that I can write this dA mu, the total path integral, in terms of something which describes only the orbits, and that will be irrelevant volume factor, and something that has the physical degrees of freedom, and we do a path integral over all possible physically inequivalent configurations. And so this is what is going to be the relevant for us. What you want is this segregation, and since this path integral is an infinite dimensional degrees of freedom we are talking about, so what we will do to see all the mathematics that we require behind it, we will use a simple two-dimensional example to illustrate this separation of relevant versus irrelevant degrees of freedom. So let's move to this two-dimensional example. So consider I have this integral to be performed where w is some d to r exponential I times s, which is a function of r, and that is rotationally invariant. So here r vector is just r theta, the doublet, and r vector subscripted with phi is a vector r which was rotated by angle phi. So to begin with, I choose any vector, and of course that has to be parameterized in terms of the modulus of the vector and the direction in which it is pointing. But I take the same symbol, and if I suffix it with the symbol phi, it means it's a rotated vector, same vector rotated. And what it tells me that s of r vector is same as s of r phi vector because of the rotation invariance. So if I rotate the vector r, it should not change my action, the function s over here. So what we wish to do is to sum over contribution from all the inequivalent s of r. Okay. In this simple example, there is an overcounting of each of the inequivalent s of r by a factor of 2 pi. Okay. and the volume factor of the redundant degrees of freedom this turns out to be. While for the gauge field theory, it is infinite number of degrees of freedom. So what we do, we insert this quantity, which is identity equal to d phi delta theta minus phi. So when I do integration over phi, it just puts the variable phi value equal to theta, and of course this here integral is all over the 0 to 2 pi, then this integral will be 1. So when I inserted this w in the expression for w, I'll take d phi outside, and then d2r is written as dr d theta exponential I times sr times this delta theta minus phi. This particular object I define as w of phi. Okay, so eventually what I have is integral over d phi w of phi. Now w of phi is computed by fixing theta to phi, and then we integrate over all possible value of phi. So w of phi is what called relevant, and phi is an irrelevant quantity, is separated out by doing this, putting this delta function. And here what we have done, that here theta, so here what we are doing, instead of integrating over all possible space, which is a full configuration space, I say that let's integrate along this line where the theta is equal to phi, and then the phi is just separately integrated outside. Okay, and I don't really care for that integration, so this is my irrelevant degree of freedom, which I needed to throw out anyways. So first I have to do segregation, and then, well, throwing out what would mean is that it gives me a constant contribution, and any correlation function in field theory doesn't depend upon the overall constant that appears in the path integral, because we always have the same factor appearing in both numerator and the denominator, and so all those constant factor will anyway cancel out. So it's as if it was never there. Okay, now so using the invariance of S of R that we started with, one can actually prove here that by w of phi and w of some phi prime, they're exactly same, they're exactly equal. Okay, so basically w of phi is a w subscript phi is a rotationally invariant quantity, so my w of phi actually doesn't depend upon the phi. That's what it means. Okay, so it can come out of the integral, and this d phi will just give me 2 pi factor. So here theta equal to phi was a gauge fixing used in this example, and one can choose a more general curve in r theta plane that cuts each orbit exactly once. So let g of r vector equal to 0. So g of r phi vector equal to 0 would is expected to have unique solution for phi for a given vector r. So if I give a vector r, okay, then I say that if you rotate it by some angle phi, then my g of phi will be 0. Okay, so let's say I wanted to do, instead of this straight line in the r theta plane, I'm integrating over this some other curve. Okay, so what I want is delta the g of r phi to be 0. So g of r phi, if I want to be 0, so I have to put that as the argument of the delta function. Now if you have some function inside the delta function and integrate over the variable this thing, then I have this derivative of this g at whenever g equal to 0 appears. So by putting those appropriate factor, this identity can be written as this derivative term, the del g r by del theta when g equal to 0. That's sort of Jacobian of this transformation. It will sit over here, and d phi del g of r phi will be sitting over here. So this is equal to 1, and let me define this Jacobian thing as some delta g of r. So I can bring it to the left hand side. So delta g of r inverse is d phi delta g of small g of r phi. This is what we have. Now additionally, we can say that this particular quantity, this delta, is actually a rotational invariant quantity. So how do I know it? Is that just rotated by some phi prime. Okay, so delta g of r phi prime would mean that this d phi delta g of r phi plus some phi prime. I should have written phi prime, not phi double prime. Let me just make that correction. Okay, so r phi plus phi prime, because I rotated the whole system by an angle phi prime. Let's say phi double prime is an angle which is equal to phi plus phi prime. and under this change of variables, the d phi and d phi prime, so to say this Jacobian for this transformation is same, is 1. So d phi can be written as this d phi double prime, because it's shifted by only a constant. Okay, now this is expression where exactly as this delta exacts that instead of phi being the dummy variable to be integrated out, phi double prime is a dummy variable. So basically this expression is this. So one can see is that my delta, capital delta of r, is a rotationally invariant quantity. So that's important thing to note, because we have to write everything in terms of, we have to use a rotational invariance everywhere. So my delta is a rotationally invariant quantity. Okay, so what I do, I insert this identity which I just wrote over here, identity equal to delta times this d phi of delta function, okay, into the expression for w. What we get is w equal to this d phi comes out, and dr d theta, this exponential isr which was to begin with there, and then I have this delta g of r and this delta of gr function. Okay, this delta function over here. And again, since this guy, my new w phi, is rotationally invariant, because this guy rotationally invariant, this guy rotationally invariant, and this delta function is also rotationally invariant. Okay, well, delta function is not rotationally invariant. Delta function times this d phi is rotationally invariant. So this guy I can say is rotationally invariant, and that will just give me some value, and the same value for each value of phi. Okay, that's more important. So overall factor of 2 pi I'll get. So what we have to do to remove the irrelevant volume factor, what we have to do is two-step things. Insert a constraining delta function, that is my gauge fixing condition. Here it is, this is a gauge fixing condition, and then multiply by the Jacobian of the transformation. Okay, so here is my Jacobian of transformation. This 2D example is extendable to QFT with infinite number of degrees of freedom. So this is a simple way I am doing the segregation. Now this is possible, one can simply port it to the gauge theory. So the rotation invariance goes to the gauge invariance. The rotation parameter phi goes to the gauge parameter theta. Okay, so the non-abelian gauge field theory is what we will start with, because abelian will be a special case, will be discussed in the last page of this lecture. So for the non-abelian gauge fields, this mu goes to mu theta. Okay, and mu double line mu, just want to remind, is mu a ta. So ta is already included over here. So mu goes to mu theta, and mu theta is written as this u theta mu minus I by g u inverse del mu u inverse. Okay, where u is exponential of minus I theta a ta, is an element of the group, where a runs from 1 to n is the number of gauge boson in the theory. Now what we have to do is, for a given mu theta forms forms a gauge orbit by varying theta a. So again we have the same task. For quantization we needed to restrict this mu a to a hypersurface where fa of mu is 0. That this particular hypersurface is the definition of this. So the hypersurface is such that it interacts with each gauge orbit exactly once. Okay, so this is the word, and in other words the same statement is made, is fa a mu theta equal to 0 has a unique solution for theta for a given mu. Okay, which was very much similar when we said over here that g of r phi equal to 0 has a unique solution for phi when a r vector was given. So here we have exact same situation. This is how we fix the gauge. The uniqueness is important so that one can invert this thing. Now let's look at the gauge parameter space. So gauge parameter theta a each of them is real, so it belongs to Rn, but it's not full Rn, it's a subset of Rn. Okay, and Rn is such that for every theta a element of this D, which is a domain, okay, the u of theta a is an element of the group. Also, for any theta 1 a and theta 2 a element of D, u theta 1 times u theta 2 can be written as some u theta 1 2, where theta 1 2 is again an element of D. Okay, so this is important property that we need to prove the invariance. To say that d theta, the path integral d theta x is a gauge invariant measure of the group parameter space D. So d theta 1 is equal to d theta 2 is equal to d theta 1 2. So this is exactly the same statement that I'm making, where I'm saying that the d phi is equal to d phi double prime. Okay? So the integral over the irrelevant degrees of freedom, which is going to be this guy, is the same. This is the invariant, is a gauge invariant construct. Okay. So need to insert this infinite dimensional delta function. So here's the infinite dimensional delta function. That's why I needed this d. So to say, this is a kind of path integral. So I'm doing integral over every single value of theta at every point in this in the x space. So this is d theta of x. Okay. Now of delta f of a theta mu. Okay, and this is equal to this delta inverse written on the left hand side, delta inverse f of a. This is the definition. Okay, where now if I write it like this, so this delta f mu is supposed to be the derivative of f. Okay, so if I just say so, and this delta is not just derivative, my apologies, this is derivative would be a matrix, and this Jacobian is just the determinant of that matrix. So this delta is this determinant of some, say, mf. Okay, where m f x y a b is del f a by del theta b. Okay, so f of a theta mu x, so x is appearing in the numerator, and delta theta b a function of y. Okay, so this is a very complicated matrix. In a ab is a countable indices, but x and y are continuous variables. So this is a matrix, or it will appear to be a differential operator in the continuum, as we will see later. But for the purposes here, let's consider it as an infinite dimensional matrix. So mf is a response of fa to the infinitesimal gauge transformation. That's what it will be, because we can always write f of a theta x is equal to f of a x without the theta plus d4y mf xy ab theta by plus order some theta square. So I can always write this response function kind of thing. Since LHS is 0, this guy is 0. Okay, I want to set it to 0, and for a given f of a, then since this guy I want the unique solution for theta b given this f of a equal to 0, that it means that for that determinant of mf here cannot be 0. So this must be an invertible matrix. Okay, so and that makes sense, because I want Jacobian to not have a divergence over here, otherwise I won't be able to write this equation itself. Okay, the determinant of mf, which is, so to say, delta, is not equal to 0. So again, next we try to see is that this delta a mu, what we saw earlier in that case, it was a rotation invariant quantity. Here we want to see that it is a gauge invariant quantity. So do a gauge transformation using u theta 2. So a mu goes to a mu theta 2, a mu theta goes to a mu theta 1 2. Okay, that just left hand side becomes del inverse a mu theta 2 integral over d theta of this a mu theta 1 2. But since d theta is same as d theta 1 2, okay, that invariance was there. So it is just same variables are integrated out, because it's integrated out over all possible theta, and hence this it comes back to the delta inverse thing. So delta inverse, or hence the delta, is a gauge invariant quantity. Now we have all the ingredients to write down the path integral for the gauge Lagrangian. Okay, so the final step is that I write this quantity z, okay, which is the d a mu ax, so all the path integral, all the gauge configuration of exponential I d for x Lagrangian for the non-abelian case, which is also called Yang-Mills field. So that's why I'm writing. So that here is where I insert this identity. Okay, where this delta inverse, so delta will be on the right hand side. So identity after doing the insertion. So this is integration over all the gauge parameter, and here is integration, same integration over all configuration remains. Then comes this delta thing, which is the determinant of mf, and here the delta function containing the gauge fixing condition times this guy. Okay, so here delta f of theta is appearing where, sorry, f of a theta is appearing while everywhere else is f of a appears. So what we do, we use the gauge invariance of all the things, like this is gauge invariant, this Lagrangian is gauge invariant, this measure is gauge invariant, okay, and this measure is gauge invariant. So we use all that to just do a transformation only locally over here and just replace a mu theta with a mu. So my z is now written as this d phi theta, which is the volume of redundancy, times this d mu a with this capital delta f mu, and then delta function of fa times this the exponential is. Okay, the s is the action over here. So I have done all the segregation, and this particular piece I call is z0. Okay, so this is my the partition function, or so it's a path integral thing, partition function that we were doing. That is when the current is set equal to 0, the source term. So here I write in terms of the source term, so just as z piece, not the overall volume. So z of j is equal to d mu d a mu ax. So this is the path integral for all configuration of this capital delta f of a mu, delta of fa a mu, times exponential of this L Young Mills, and this j mu a mu a. This current term is added, and this is particular thing is called what's called the Faddeev-Popov ansatz, that this is the path integral that we should have. Okay, and now what we need to do is need to handle this delta factor and the delta function in a proper manner. Okay, so as we saw previously, that we have to just whenever we want to do this segregation, or like put the gauge condition, we have to put the delta function, put the Jacobian factor, and all this spurious factor will fall off, so will be separated out, and so we are interested only in this piece. Okay, so let's now go one by one and check how to handle these two pieces. And the way I can already say that the way we have all these things written is exponential of action. If I can exponentiate these two factors, then I can just write them as some additional terms into action, and integration over some path integral over some other set of variables. So it will look exactly into the it will fall into the place the way all the techniques of path integrals are developed, so I will be able to deal with them. So the rest of the exercise is how to exponentiate these things such that I can write it as a path integrals. So let's remind ourselves is that this delta f of a mu is determinant of some matrix M, where M was this first derivative of the gauge condition with regard to the gauge parameter. Okay, so this is what we have to write. Now what we do is that let's consider the action for a complex field CA, where and I'm call it S Faddeev-Popov, SFP, equal to d4x d4y c dagger a x m f x y a b c b y. So let's consider this. Okay, and let's consider this action, and let's consider this particular path integral, and then we say this particular path integral is equal to determinant of mf. I want, so that I want to write this mf as this particular path integral. The above path integral makes sense if CA and CA dagger are the Grassmann valued variable. Okay, because we know if it is ordinary real and complex number, then path integral will have 1 over determinant of this matrix. But since I want the determinant of this matrix, so while exponentiating, so doing it using it in reverse way, I want these fields over which the path integrals were performed, they have to be Grassmann valued complex field, okay, or complex Grassmann numbers. And additionally, CAX is a scalar under Lorentz transformation. It's not a spinor. It doesn't satisfy Dirac equation or anything. Okay, and so since it's a Grassmann valued thing, so it obeys the Pauli exclusion principle. And as we can see, this field we didn't have to begin with, so we are putting that field back in here to exponentiate a matrix. So basically it's an unphysical auxiliary field. Okay, so this is and it's called the Faddeev-Popov ghost. The reason for calling it ghost is not because it's unphysical, it's because it has a ghostly property. It's supposed to be a scalar, Lorentz scalar, and yet it has to satisfy the Pauli exclusion principle. Okay, so once we have this setup, then we can say that delta f can be exponentiated by adding SPF to the action. So it is just this delta IMF is nothing but this. It's equivalently saying over here that you added a term to the action. Okay, and likewise we can handle the gauge fixing term. So this s of so this delta of f of a can be exponentiated as follows. It's a set of steps. What we do, instead of saying that I am going to add delta, so f of a equal to 0, I just say choose a gauge fixing condition in slightly modified manner, which is to say fa of a mu theta equal to some b of x. The b of x is independent of the fields and depends only on the x mu. Okay, so modify the delta function to be 1 equal to this, the path integral over all the gauge parameters times delta f of a mu, which will remain same because it's a derivative of this guy, the derivative of the argument with regard to theta, and since b is independent of theta, it is same as the derivative of fa. So this expression remains unchanged by changing this delta function. So this delta of fa theta minus ba is what appears. Okay, so and if I introduce this into the action, then instead of having this delta of f of a, I'll have delta of f of a minus b. Now additionally, what we do, we introduce another constant. So introducing any constant into the path integral will not have any physical significance because this constant will cancel in numerator and the denominator while computing any endpoint correlation function of the physical fields. So what I do, I introduce another auxiliary field dA. Okay, and just say integral over dBA. This is a standard bosonic field, so scalar actually. So dBA integral exponential minus I by twice I d4 BAX whole squared. This would give me some constant. Okay, so if I introduce this constant and then integrate out this particular guy to get rid of this delta function. Okay, I keep this factor alive, but I just integrate out this delta function by introducing this. Okay, what end up happening is that BA is replaced by f of a. So I effectively get this particular factor in that in the path integral. So this is equivalent to having this adding this additional term into the action, which is called the S gauge fixing, is minus 1 by twice xi d4x f of a mu x whole square. This is the term that get added to the action of the Lagrangian. To sum up, what we have done is to exponentiate delta by means of the path integral over Grassmann valued ghost field CA, and exponentiated delta function using Gaussian representation of delta function. So this is another way to say that delta function can be written as a Gaussian thing. So I could have directly substituted that, but this is a more cleaner way to argue this. Okay, and here also some harmless constant will come, which is exactly what we are talking about here. This modification to this action, this leads to modification to the action, and hence the Lagrangian. So my Zj is just dA, dc is dagger dc, because the exponentiation of the delta function did not add, well, we added a path integral, but then we integrated out explicitly to get rid of this delta function. So there is no leftover path integral coming from there. So I have dA, dc dagger dc, exponential of some s effective, and then is the source term for the a mu. That is the Zj that we will have. The s effective is minus 1 by 4 f mu a f mu a, which is the action, which is a sorry, this is, I should have written over here. This is L effective. Maybe I just write d4x. Oh well, let me not mess up this thing here. I'll correct this later. So this is basically the what I wrote over this particular piece has to be d4x integrated. Okay, so now whatever we came up till here, it's for a general gauge fixing condition f of a mu equal to 0, and only condition that was there, that m has to be invertible, so gauge fixing condition has to be treated appropriately. Okay, so it is instructive now to look at the explicit examples, and we'll be looking at two examples, which is covariant gauge, which is del mu a equal to 0, axial gauge where a3 a equal to 0. So it is a third component of gauge field for every value of a is set equal to 0. Okay, so let's look at, so the last one is not covariant, but let's look at the covariant gauge, which is f of a mu del mu equal to 0. So my infinitesimal transformation u of theta x is can be stopped at just theta, and this is the way we have written in our gauge invariant when we introduced the non-abelian gauge theory. And under this transformation, a mu theta, so the transforms guy, a mu a theta, it can be written as a mu a, fabc theta b, a mu c, minus 1 by g del mu theta a, plus higher order term in theta can be used, can be written, because this u of theta has further terms over here. Okay, now if I just stop at theta, then I'll just have the standard form that we have been using in well, that we also are using for the small theta. F of a theta is just del mu a theta, so just act with del mu over here for the term, so del mu a mu a, and then del mu of this piece plus order theta square. Now I can exactly write in terms of the linear response way of writing it, and extract that mf x comma y a b is just minus 1 by g del mu delta a b del mu minus g, so this g cancels. This is just this particular operator written over here, okay, with delta x minus y, because if I do integral over dy, okay, so I have to get rid of this delta function by that will put y equal to x. Okay, so whatever is sitting on the y, the theta by will become theta bx. Okay, that's why we need this delta function, and this delta ab just to make sure that here it was a theta a and we are taking out is theta b. Okay, so this is my m, and what we note is that m depends upon a mu c, that is not a constant matrix. We talked about earlier that if this thing were just a constant matrix, then I need not exponentiate it. Okay, so what happens that since it does depend upon a mu, it's not a constant matrix, it leads to a non-trivial action for the Faddeev-Popov. That means a non-trivial modification of the action. So let's look at what it is. The Faddeev-Popov action will be minus 1 by g d for x. C twiddle diagram, I'm just writing C twiddle instead of C because I need to rescale it. Okay, so C twiddle A diagram, del mu delta AB del mu G FABC A mu C, and I should have written a delta function also here. Okay, that is already integrated out. The delta x minus y is integrated out to write this CBY into CBX twiddle. Okay, and this is a Grassmann value field. Now we'll define CAX equal to 1 by root g of this CA twiddle to absorb this 1 over g over here, and then I just have this nice looking matrix. Okay, so now I can just say the kinetic piece of CA is just which has two derivatives, so just this piece multiplied by CBX. Okay, so it basically becomes CA x del mu CAX and over minus sign. If I perform integration by parts and throw away the boundary term, I have del mu CA diagonal del mu CA. Okay, so this is like leads to a propagator of the CA field. So my ghost propagator turns out to be I delta AB by k square plus I epsilon. There is no mass term for this ghost field. Okay, so there is a massless scalar which satisfies the Pauli exclusion principle. Okay, and it has a non-trivial gauge interaction. So this is the gauge interaction piece, which is G FABC as CAX del mu AC mu x CBX. Okay, so what is the important thing to note over here is that despite being unphysical, ghost fields do propagate and interact with the gauge field. Now them being propagating is not a big deal, as I will explain in a moment, that it can have a non-trivial it can have a propagator, but what is more relevant, that why I cannot simply integrate out C and throw it away, is because they interact with gauge field. That was the thing, that my MF is not a constant. I can't simply throw this away. I had to exponentiate it and write in terms of the gauge field, the interaction with the gauge field. Okay, So this, but what happens is the propagation and the interaction of with mu are gauge dependent feature. If I change the gauge, of course, the nature of propagator of ghost field will change, and the interaction will also change. And we'll see one example for the axial field. Okay, so right, so this is what we wrote is the SPF, SFP, the Faddeev-Popov term. Next thing, of course, is there is a gauge fixing term, and gauge fixing term is just minus 1 by twice xi T4x del mu a mu a del mu a mu a. Okay, now we already talked about the ghost propagator. Now we can talk about the gauge field propagator. So if we look at just the quadratic part of the Lagrangian, okay, so then it is written over here. So this is coming from 1 by 4 f mu a f mu a, and this is the part coming from the gauge field that we just wrote. Okay, here I can perform the integration by parts to write a and a on the side and del operator in between, and the exact same thing is done for the part that comes from the Young-Mills Lagrangian. So I can write this as half a mu a p mu nu a b a nu b. Okay, where p mu nu a b is just g mu nu del square minus 1 by 1 minus xi del mu delta a b. Okay, so this is the operator that I need to write in the momentum space first and then invert it. So this is just a momentum space expression, and this is invertible and it does not behave like a projection operator because this extra xi, this we already saw when we're talking about the quantizing this gauge field. So what we get is a gauge propagator is minus I delta AB by k square plus I epsilon g mu nu k square minus 1 minus epsilon k mu k nu. And this is for general xi value. And now here, as I said, one can choose xi equal to 1 to simplify this term in one way, and then set xi equal to 0 to simplify this term in another way. So this again we have discussed. So this is my gauge propagator for a non-abelian gauge field theory. Now moving on to next gauge, which is the axial gauge. We see that f of a is equal to f3 of a equal to 0 for all a. This is my condition. So this condition does not appear to be Lorentz invariant, but all the physical quantities should not depend upon the details of the gauge choice, because a gauge invariant theory should not have the results, physical result, depending upon the gauge choices. Okay, so this supposed Lorentz invariant, not having the Lorentz invariance is actually not concerned. In fact, there is a way to write this in a Lorentz invariant way, which we will have either in the homework or some discussions. Okay. So f of a mu a equal to a mu a theta 3, which is written as a3a plus fabc theta b ac 3 minus 1 by g del 3 theta a. Now since a3 is 0 for all value of a, so this is 0 and this is 0, so these two terms are 0, so my condition basically becomes for a given theta to be just minus g del 3 theta a, and that gives my mf x minus y ab to be minus 1 over g del 3 delta av delta 4 x minus y. So nowhere here mu appears. So this is independent of mu. That means determinant of mf is a constant and can be ignored in the path integral. In other words, no need to exponentiate mf to begin with, so no ghost in the theory. Or we exponentiate to get the ghost, but it does not interact with any other field, so as if it wasn't there. We'll never know, it will never appear in any computation of any physical quantities. Now, after having discussion with this, talking about abelian gauge theory becomes really trivial, because in abelian theory we have a mu theta equal to a mu x minus 1 over g del mu theta. Okay, no approximation, this is it is. Okay, there's no leading order in theta, this is a complete gauge transformation. Okay, so we note here that there is no cross term between theta and a mu in here. What happens that I will not have, so that means that as long as f of a mu is linear in a mu theta, then mf will be independent of m. So all I need that the gauge conditions are linear. So for linear gauge conditions, abelian theory is just ghost free. Okay, there will be gauge fixing term as it is and same kind of propagator. Okay, but this gauge where there is no ghost field and for the linear choices. Okay, And usually gauge fixing condition, both the Lorentz condition, so the covariant condition and the axial condition is linear in it. So we will have abelian theory completely free of the ghost. So we actually can exponentiate any constant as a Gaussian like path integral over some field that do not interact with any other field. Okay, so this is an auxiliary field is what we have to put over there. An auxiliary field that does not interact with any other field or itself can be completely integrated out without changing any physical quantity. That means endpoint function of the physical field. Okay, so here what we discussed, that a non-abelian field theory and also the abelian field theory can be quantized using path integral formalism. We have to put the gauge fixing condition, and that requires us to introduce a ghost field in case for certain gauge choices for the non-abelian only, and for abelian, as long as the gauge condition is linear in the gauge field, we don't need the ghost. Otherwise we'll have to have the ghost here as well. Okay, so with this I finish this lecture, and in the next lecture we'll talk about interacting field theory. So we see that the Yang-Mills theory does have the self-interaction of the gauge boson, but here we were not computing the partition function. Here we are only writing the partition function and various terms in the action. We are not performing any actual computation. Okay, so for performing any actual computation, we only look at the quadratic pieces of everything. Okay, only the quadratic pieces, and all the interaction has to be treated separately. And we have already discussed the computation of the free part along with the source term, and how the functional derivative gives a range of correlation functions. So that theory will carry over. So first we have to write a general theory. We'll discuss the general interacting theory, and then we'll take the free part of that and write in terms of the functional this integrals, and the functional derivative of this generating functionals will give me all the Green's function. So that would be in the next lecture.